Invitation. It's really a pleasure to be here in Toronto, exploring the city and hearing these great talks in honor of Professor Birkar. Let's see. So in birational geometry, and maybe I should say everything today is joint with Nathan Chen, Benjamin Church, and Lena G, or some subset. And please feel free to interrupt me. I love an active audience. Let's see. So in birational geometry, we have this trichotomy of building blocks. So we have Fano varieties, which kind of look like donut holes. We have Calabi-Yaos, which look like donuts. And we have general type varieties that are donuts you can share. And so these are sort of building blocks in birational geometry, and one of the main distinctions between these donuts is they're distinguished by their holomorphic forms, or the nature of their global holomorphic forms. So let's start by just thinking over the complex numbers and just thinking about hypersurfaces. So today I'll be mostly talking about Fano varieties, and Fano varieties are the ones that don't have forms. So if we're looking over the complex numbers, and we have a smooth Fano hypersurface, well, what do we know? So we know that because it's smooth and Fano, then the degree is bounded by n+1. And so I think when I was first learning about these things, I think the motto I learned for Fano varieties is that Fano varieties are like projective space. Okay. So a lot of the aspects of birational geometry of these hypersurfaces are like projective space. So if D is, which is the degree of this hypersurface, let's see, smooth hypersurface of degree D. So if D is 1, 2, or 3, and imagine n is at least 3 or 2, then these are always rational, right? So in particular, they're like projective space, so phi is rational. And so sometimes, that's a very important word. Okay, I'll have to remember sometimes. And these are always rationally connected. So through any 2 points, there's some rational curve. And they don't have any holomorphic forms. Sometimes these things are unirational. So a different sort of sometimes. So these are the only ones that we know are rational, but at least when 2D factorial is less than n, so this is a result of Beheshti-Riedel, then sometimes they're unirational. Okay. On the other hand, I think maybe the point of this talk is to ask the following question: is X like Pn? And so, of course, sometimes it is. But the rationality question asks this right on the nose. It says, well, when is it rational? So it says, for which D into n is X rational? Or rather, not rational. And I don't think we really expect there rational that often, and we have good evidence. So Kolar proved that if D is at least 2, this function, so the ceiling of n plus 3 over 3, and x is very general, so I should say that, and x is very general, then x is not rational. Okay, so functions like this will appear in my talk, so maybe I should just say what they are. So this is roughly 1/3 of the degrees in the Fano range, but it's just a little worse than that. So it's a little less than 1/3 of the degrees, and it's the top third. Okay? And Schreider recently gave a vast improvement to this result and proved that if D is at least log 2n plus 2, and x is very general, then again, x is not rational. So we know a lot of the times that these things are not rational, but there's many aspects to birational geometry, and it's not just, are they the same? And I think my motivating question for this talk is, how does the birational geometry of these hypersurfaces differ from the birational geometry of projective space? Question. So how does the birational geometry of x differ from the birational geometry of projective space? And obviously, this is a very open-ended question, and so you have to decide what aspects of birational geometry are you interested in. So I'll start with one that I am interested in. Maybe, are there any questions? So if we're thinking beyond just the rationality problem, one question we could be interested in is, what rational fibrations does X admit? So let me mention first the theorem of Kolar. Which you could also think about as this rationality theorem. What Kolar proves is that if X is very general and of degree D, and if D is at least 2, for at least 2/3 of the degrees in the Fano range, we know that X is not ruled. So ruled is the same as being birational to Z cross P1 for any Z. So Kolar proved that, and in particular, this implies they're not rational, right? But so you could think of this theorem as saying we don't have any Zariski locally trivial fibrations in P1s. And so if you're thinking about it that way, then you can ask, what about conic bundles? And Kolar also tells us something about conic bundles. Kolar proves that if D is at least 3n plus 3 over 4, then X is not birational to a conic bundle. Okay. In other words, it doesn't admit fibrations in P1s, right? And so this is something you might be interested in if you're interested in sort of the birational geometry from the MMP perspective. It says there's no Mori fiber spaces of relative dimension 1. Or if you just care about curves, it's also interesting So let me just jump right to one of our theorems. Right away, so what we showed in a paper that came out in September, I think, maybe it was August. So in the setting of these hypersurfaces, if X is very general of degree D, and D is at least 5 n plus 3 over 6, so this is a sixth of a Fano range, right? So what do we get? Then X is not birational to an elliptic fibration. We prove more. We also consider higher genus fibrations, but the numbers get a bit messy, so let me not put them down. So just say a remark. We have results for higher genus as well. Okay, and so to me, at least from the MMP perspective, one interesting application of this theorem is that then you can show that X is not birational to a del Pezzo fibration. Oh, so this is our theorem. Yeah. The corollary so in this range, so if D is at least 5m plus 3 over 6, then X is not birational to a fibration in smooth del Pezzo surfaces. So this is really immediate. And the point is, whenever you have a del Pezzo surface, so if you have a smooth del Pezzo surface, then you can just consider a general pencil and minus the canonical. So a general pencil in the minus k linear system is an elliptic fibration. And so then you can, if you have some fibration in del Pezzos, you can go to the generic point and spread it out, and then you get this elliptic fibration of your original hypersurface. Okay? Yeah, that's right. So a fibration that's generically smooth, yeah. So not such a strong assumption. Yeah, so I don't mean that every fiber is smooth. Yeah, so I want to mention that, so a different way you can think about this question about how the birational geometry of these hypersurfaces differs from projective space is you could ask about all the Mori fiber space structures. And so there's a lot of work by, let me name some authors. Mike, there's lots of work by Ferney, Buklikov, Iskovsky-Manin, and others who considered sort of the birational rigidity of index 1 hypersurfaces, right? And what they show is that actually these index 1 hypersurfaces, they're not birational to any Mori fiber spaces. And so this is sort of a much stronger version of the theorem that we've proved, because we only look at Mori fiber spaces in sort of relative dimension 2. And so let's see, so prove birational rigidity of index 1 hypersurfaces and Puklikov also has some interesting results at index 2. Puklikov shows that the only Mori fiber space structures on an index 2 Fano hypersurface are the map to a point and also pencils. And that starts when n is at least 14, so pretty high. So for birational rigidity, that's right. So it's for all smooth things and some singular things too. So these methods are certainly more robust in some sense. Okay, so my title mentioned 2 characteristics. So I wanted to discuss how we sort of involve characteristic P, and this goes back to Kolar's idea. So Kolar's idea is to sort of spread these hypersurfaces out over mixed characteristic, and then use a specialization construction of Mori to mu p covers in characteristic P. So use Mori specialization of hypersurfaces to mu p covers in characteristic P. And I'll go into some detail about this. So, and then the idea is that there's some exotic geometry in characteristic P that you can use to control the birational geometry in characteristic 0. So for example, so how do hypersurfaces degenerate to these mu p covers? So if we're just looking in characteristic 0, you can still think about this. And so if we imagine a quartic polynomial and a quadratic polynomial, in 3 variables, so if these are general quartics and a general conic, then you can write down a family that looks like the following. So you can write T f plus q squared equals 0. So this is a family of curves, of quartic curves that's parameterized by time, right? And as you degenerate to t equals 0, what happens is you degenerate to this double conic, right? But what we know, because that there's this Deligne-Munford moduli space of smooth curves, we know that there should be some stable limit of this family. And of course, it's very classical that this is a family of non-hyperelliptic genus 3 curves that's degenerating to a hyperelliptic genus 3 curve, if these things are general. And so this hyperelliptic thing is something that has a mu2 cyclic cover over the conic. Okay? And you can imagine it's not so hard to construct these families in mixed characteristic as well. If you replace t by a 3, right, then you can reduce mod 3, and you have a double cover. And you're degenerating to a double cover in characteristic 3. Okay, but let me just write down Maury's equations as well. Because I think it's kind of nice to see what the global equations look like. So you start with, say, a DVR. DVR with uniformizer pi. And let's say the generic point, or the residue field is kappa. And the generic fiber is eta. Okay, so you can construct the following degeneration of hypersurfaces inside a weighted projective space. And so it's not going to look like hypersurfaces because I'm going to give you two equations. This is a P. So this is a subset of the weighted projective space 1, 1, 1, P. Okay, so I have n plus 2 x variables. My degree of my f polynomial is degree p times e. And the degree of my g polynomial, the degree of the polynomial g is 3, is e. And so in words, this is a degeneration of hypersurfaces in projective space to a mu p of hypersurfaces of degree pe in projective space to a mu p cover of a degree e hypersurface. Let's check. So, yes. Thanks. Good catch. Okay. Okay, so let me just write what I said in words. So x eta is isomorphic to a hypersurface of degree pe in Pn plus 1 eta. And then x kappa is isomorphic to a mu p cover of a degree e hypersurface, which I'll call y kappa. Okay? And it's not too hard to see, and you can really see it from this weighted projective space, that this mu p cover lives inside the total space of a line bundle. So there's some factorization here. We have x kappa, this mu p cover down to y kappa. But it factors through some line bundle. And now if kappa is mixed, if kappa is in characteristic p, then a mu p cover is something interesting because it's a purely inseparable cover, right? And so this is some exotic geometry that we don't have in characteristic 0. At least it's exotic if you live in characteristic 0. And Kolar wants to take advantage of this. Okay. So you can try and draw a picture of this. You probably shouldn't, but I will. So we have this line bundle. We have x, or we have y kappa. And then we have this purely inseparable cover. Okay. And if you haven't seen these things before, even though it looks like x kappa is non-reduced, it doesn't have to be non-reduced. And it probably isn't. And Kolar's observation is, well, we should look at the forms that you can construct on here. And then there's some obvious forms that you can get. Maybe obvious is a strong word. Okay, so how do you get forms? So let's name my map pi. So the only thing I know how to do is look at the pullback of the space of differentials on y, right? And what do I know? So I know that this map is purely inseparable. And so what that tells me is that the map is identically 0 when I take the determinant on the derivative, right? So I have some map here. This is x kappa, right? And I know it's not full rank. So this drops rank, and this actually has co-rank 1. It's not hard to see it has co-rank 1 because it factors through this smooth line bundle. Okay? And so because it has co-rank 1, it factors through its image, which has some rank n minus 1. Okay? And roughly speaking, this image sheaf is a source of n minus 1 forms on X. So let me write Kolar's theorem. Are there any questions? Questions? Okay. So Kolar proves that if n is at least 3, and Fg in this sort of Mori's family are general, and E is at least n plus 3 over p plus 1, then the determinant of Q, this sits inside wedge n minus 1. And moreover, it's the pullback of a very ample line bundle on y kappa. Sorry, this is very low. Okay. So we have forms. And I think the whole moral of this talk is that forms are very powerful. So a corollary, an immediate corollary, is that we have forms. And x kappa is not ruled. Okay, let me make 2 comments. So the first comment is that this theorem as stated is a bit of a lie because x kappa itself has some singularities. They're isolated singularities, they're resolvable, they're just little gnats floating around, you can take care of them, but as stated, it's a small fib. And the second comment I want to make is it's not totally obvious then why is x kappa not ruled, right? So ruled varieties, they can have n minus 1 forms, right? So even the rational things or rationally connected things don't usually have n minus 1 forms. Ruled things can have n minus 1 forms because if you have z cross p1, you can pull back n minus 1 forms from z. Okay? But the point, let's draw this picture. So this is z and this is z cross p1. is if I pull back n-1 forms from Z, they can't separate points on the fiber, right? And so it's not just the forms, it's also the positivity of the forms that help you control the birational geometry in this situation. Okay? Any questions? Okay, so now we know that the special fiber of Mori's specialization is not ruled. And then you just apply this theorem of Matsuzaka, the Matsuzaka's theorem. Says that if, roughly speaking, if x eta specializes to x kappa, and x eta is ruled, then x kappa is ruled. And you should make some assumptions about this family, and in fact, we really want to talk about the geometric generic fiber rather than just the generic fiber in these families, but it's all okay. And this implies Kollár's non-rationality result. Okay. So what is the point that I really want to make today? The point is that it's not just this. It's not just that you have forms in characteristic P. It's also that you have this positivity in characteristic P that really lets you control this birational geometry. So it's the positivity of the forms that are powerful. Okay, so what's another example? So if you're interested in fibrations and curves like I am, if you have some fibration in curves, and let's say you know that this general fiber has some n-1 forms, you can contract these n-1 forms to give forms on this curve. So the n-1 forms on the total space contract to forms on the fibers. And you can use this positivity that you have to actually control the genus of these curves. So I think this is an argument that's very believable in characteristic 0. And if you're trying to make this argument work by degeneration to characteristic P, you should be aware of some of the subtleties of characteristic P geometry. So one of the characteristic P issues that you run into is that you can have regular families of singular curves. So where the total space is regular, but the general fiber is a singular curve. So there exist regular families of singular curves. So again, to draw a picture that I shouldn't draw, I have a bunch of cusps. Okay, so how do you actually deal with this? And as far as I know, I don't actually know a way to directly use these forms to rule out such families. We don't know how to do this. So the thing that we do is we avoid these families. And so how can you do this? So what you can use is what's called Tate's genus change formula. So if you ask, I can try and tell you what it is, but I won't if you don't ask. What this does is it says you don't have to worry about these such regular families if the genus is small compared to the characteristic. So for us, genus 5, or characteristic 5 was good enough to take care of genus 1 things. Okay, any questions? Okay, so this is a very specific aspect of birational geometry, and I would say I'm interested in it. I'm not sure if you're interested in it. You can tell me after. So what are some other aspects of birational geometry we might want to compare to projective space? So what about birational automorphisms? Okay, so the group of birational automorphisms of X is just the degree 1 rational maps from X to itself. So we already heard a nice talk about the Cremona group. And I think there's lots of really great examples you can write down here. So the first example, of course, is the Cremona group of C, which is for Pn over C. So what we know is that this is a very large group. There's other good examples of varieties that have big birational automorphism groups. So for example, if you have a cubic hypersurface, there's a number of ways you can construct birational automorphisms on these things. Probably the easiest thing you can do is you can just project from a point. So obviously, projection is not a birational automorphism because it's a 2-to-1 map, but it induces a birational involution. There's definitely other sources of these things. Okay, but on the other side of things, if you're looking at a high degree Fano hypersurface, which is kind of an oxymoron, we have birational rigidity. So if the degree is n+1, is smooth of degree n+1, then X is birationally rigid, so bur X is equal to the X, which is finite. And if you're assuming that X is general, it's definitely trivial. It's easy to compute the automorphism group here. Here, n is at least 3. And this is also true for index 2 Fanos, by this Pukhlikov result. But again, that starts at n equals 14. Okay. But we know, as birational geometers, we might not all be birational geometers, but if you're a birational geometer, you know that you can use forms to control birational automorphisms. So for example, we know that general type varieties, any birational automorphism gives you a regular automorphism of the canonical model, at least over C. And so we would like to use these forms in characteristic P to also control the birational automorphisms. We'll do this in kind of 2 steps. Theorem. In characteristic P, so if x kappa to y kappa is one of these mu p covers that I'll say have forms, then the birational automorphism group is equal to the automorphism group. It's fine. And let me put into the quotes with forms a lot of the technical things that make this theorem true. Okay. So I could give you precise degree bounds on what type of covers you can do, but let me just avoid that. Pretty good. Okay, and so now we can control the birational automorphism group in characteristic P, but what does that really say about the characteristic 0 fiber? And so I was very happy to say that we could say something. Theorem. This is Chen, G, myself. So if X is very general of degree D, it's a very general hypersurface of degree D in CPN plus 1, and D is at least 5 n plus 3 over 6. Then you can use this result in characteristic P to control torsion elements in the birational automorphism group in characteristic 0. So then for X has no elements of finite order. Okay, so I'll talk about how this works. But it also begs the most obvious question in the room: what about the elements of infinite order? And so we don't have good ways to control this at the moment, but obviously I'm extremely interested, and I don't expect that there are elements of infinite order, right? Just some random hypersurface. I think that it's far from being rational, right? So I don't think it has any elements of infinite order. But if you have a ways of constructing it, that would also be interesting, of course. So what about infinite order elements? Okay, and so I didn't talk so much about how specialization works for these families of curves, but I'll say a little bit more for birational automorphisms. So what do we show? Okay, so let's work in the sort of general setup. So S is a DVR as before, and let's say XS, X kappa, X eta are the whole family, the special fiber and the generic fiber. So first off, we define what's called the specialization subgroup. Okay, so for whatever reason, it's denoted by capital C. It's a fun letter to write. So there's something called a specialization subgroup that lives inside the birational automorphism group of the geometric generic fiber. And here you should definitely assume that like the special fiber is reduced and probably some variety. It's a good thing to assume. And the specialization subgroup has a specialization homomorphism. So call it SPA. It goes from the subgroup to the birational automorphisms of the special fiber. Okay, so maybe this notation is a bit confusing. So this is a subgroup of the birational automorphisms of the geometric generic fiber, and it depends on the special fiber. So that's why there's parentheses here. And so this is a homomorphism from a subgroup of this thing to here. Okay. I shouldn't have erased that. Let's see. Okay, and then the next thing we say is we can say something about the torsion elements in the kernel, which I think is surprising. So the torsion elements in the kernel of the specialization homomorphism have order the characteristic of the residue field to some power. And then lastly, this doesn't have a name. You really need to say something about every element in the birational, the specialization subgroup to equal the birational automorphism group. And that happens. So if XR is regular, XS regular, and X kappa bar is not ruled, exactly what Kolar tells us, then the specialization subgroup equals the birational automorphism group. Okay, so putting these things together is how you prove the theorem. I think I should say a few words about this specialization map. So the elements in the specialization subgroup, they're just the things whose graphs specialize to a graph of a birational automorphism on that component that you're interested in. So that's how it depends on the component. And then the other surprising thing, maybe it's not surprising, but to us, to me, I was very happy to find this example, is that you can have elements of infinite order in the kernel. And these are pretty fun. So let me just explain an example. So if you look at K3 surfaces in P2 cross P2 of type, so let's call this X of T, of type 1, 1, 2, 2. So what do I mean? They are complete intersections of two divisors of these types. Okay, what do you get? So xt, this has two maps. And as we saw in the cubic example, these induce two birational involutions by switching the sheets of the fiber because these are degree 2 maps. What you can say is if t is general, or if xt is general, very general, then these things have no relations. Then, and they actually generate the birational, the automorphism group of xt. So it's the free product on these involutions. But maybe you see where this is going. If you specialize, sometimes these involutions commute. For special x, these commute. And so if you take something in the commutator subgroup here, you can specialize it to something that's trivial. So that's something of infinite order that specializes, that's in the kernel of the specialization homomorphism. And it's a bit early, but I think people will be happy to go. So let me end there.